So, our conversation today is about complex problems. And as soon as you talk about complex problems, people start to have different reactions. Engineers sometimes have a reaction of extreme happiness. And if you bring up complex problems with a boss, that's usually a bad thing. That'll really kind of be a people don't do that. And then you don't want to bring up too many complex problems, I guess, in your relationship as well. So we want to talk about this. So I thought it was really funny. I want to talk about complex problems, identifying them, just sort of like bringing that sort of that computer science to the forefront. And I thought it was funny to say, complex problems and other ways to disappoint your friends. So let's get started again. Who is this? This is me being very professional. This is me actually. This photo was taken with an all-team retreat with the company. I'm a CIO of a wonderful company called Infinite Red, and at this all-team retreat, it's just an opportunity, just hearing you talk a little bit about how nice it is to get everybody together and to be in the same place and have pizza and all those other fun things. It just reminds me of like how nice it is. I look forward to that. One of the things that I do when I like to do these virtual presentations is I need that sort of human contact. I need that fun. I need that energy. So giving me that energy in the chat's totally awesome. Feel free to throw some questions in there. And then also you'll sort of pick up from the vibe of the way I do my presentations. While we do talk about scientifically complicated things, it shouldn't be unapproachable. It should be fun because as an engineer, we like putting puzzles together. We like solving problems. We like figuring out the real strings of the universe and how they actually fit together. And one of the things I do with that is if you ever want to talk about AI, especially AI in JavaScript, or if you want to talk about React Native or any of those other concepts, this is something we talk about all the time. I do a lot of talks on that. Today, I'm talking about more theoretical kind of things, but if you want to hit me up on either, I would say Twitter, but now it's called my X, I guess, because I used to use that for social media, uh, or LinkedIn or wherever way you want to connect with me. Let's have a conversation together. Look for me at gantlaborde.com. That's always going to be up there. But let's talk about AI. Let's talk about JavaScript. Let's talk about React Native. Cool. Awesome. And then if you ever do have some kind of mobile project and you need to get a team together, I just have to say, I love my team. They're a bunch of like-minded, fun, cool people. We do the React Native newsletter, React Native radio. We do the conference. We do so much stuff together. So if you ever get a chance to meet the wonderful people that I work with at Infinite Red, that's a friendly, awesome group as well. So if you like me, you like them. Let's dig in. Complex problems. So I like the beauty of architecture. I live in a city in the States, which just celebrated being 300 years old. I know everybody everywhere else is just laughing at the idea that 300 is a long time. You probably have a hotel that's been around for longer than 300 years in different parts over in Europe. But one of the things I really enjoy is that you see over those 300 years, you see a huge change in architecture. You see people going from, is it possible, to it will be possible. And kids today just look at buildings and they say, oh, of course, yeah, it just has a giant wave to the left and the right and goes up. Of course, it's just, there's no math. It's not difficult. It just, you could do anything with buildings, right? But back in the beginning, people used to build bridges and try to build structures and try to make them elegant and beautiful, and they would fail, right? And the same thing happened with computers. Back in the 70s, you had to think about the complexity of a problem because your computer was so slow, you had to figure out if it would ever even solve it. And then there was just this thing called the halting problem. I was wondering, will it ever come to a solution? Will that computer just run till the end of time? Right. And so when computers were slower, the idea of like thinking about algorithmic complexity was way cooler, right? And then today I meet devs and they push back against the idea of that, saying like all the important problems are solved. I don't need to think about that anymore. It's just an academic problem. For instance, if I were to ask you, what is the sorting algorithm that you use to sort an array in JavaScript? JavaScript devs, if you don't mind, throw that in the chat. Do you know what sorting algorithm is used when you use array.sort? And the truth is, we don't have to kind of know these things anymore, right? We just kind of assume them to the point where there's not an assigned sorting algorithm even prescribed. So the answer to my question, good guess, Vladimir. The trick is it's implementation details. So JavaScript is a specification. We don't even care what they use to do the sort. We don't care, and JavaScript doesn't care. It depends on the JavaScript engine that does the implementation. So the actual answer is it depends on the engine. Crazy, right? But just shows how far we are from this idea of, hey, let's study algorithms and sorting, to who cares? And so we start to live in this world now where we measure problems. The problem isn't even complex. So can you figure it out or can you not figure it out? So we have a new definition of sort of like what is complexity, right? How do we look at problems there? And isn't it subjective? Like, couldn't you look at it in a few different perspectives? And the truth is yes, but I don't want to throw out all of academia. I don't want to throw out that sort of like things there. And so that's what my talk is about. Let me take the old books and dust them off and show you how we're identifying and solving complex problems today. Because the way people think about complex problems now is kind of weird. Like, hey, if a senior dev can't do it, then it must be a complex problem. I can't tell you how many companies I work with, that's their definition of complexity, right? But what about those of us who know about big O notation? And if you do know about big O notation, please let me know in the chat. I want to see that as well. But you go to a little bit of college and then you know that we have to do this big O notation, or maybe some people take some classes and they're seeing it. Yeah, perfect. And so we know about big O notation as a way of measuring it. And so that's different. Like, you have the person who just started says, well, if the senior dev can't do it, it must be complex. And then you have the senior dev who looks at it and says, okay, well, this is solving kind of like this way. It's like, it's big O of n, so it's kind of not that good. And then there's this whole level that just kind of jumps off in the deep end with non-polynomial time solving or exponential time solutions. And so these look like that we're just, to the beginners, that doesn't even exist to them. They've never even heard of some of these concepts. And so I think that's really important. We've got to think about that, because those problems, NP problems, sneak in, and people, I've seen this now, don't notice because they look so simple. Let's just throw a computer at it. Okay. And we're going to go through a classic example real quick. And I think that this is really, I love this example because it's so devastatingly simple. And it's one of my favorites. So a lot of you might know the problem of the traveling salesman. The first problem with the traveling salesman is that it's not politically correct anymore. It's the traveling salesperson. But it's a very simple problem. And so what I want you to pretend here is put your mindset as a developer who's just getting started with a company and they hand you a task. Okay. And it's just, feel how simple the description of this is. We're going to give you a set of cities and we're going to tell you the distance between every pair of cities. And the problem is to find the shortest route so that you visit all those cities one time and then come back to the starting point. The traveling salesperson problem needs to go to each of those cities, do a sale, and then come back to where they went ahead and started. We just need you to write that algorithm. Well, that doesn't sound complicated at all. All right. So you put the most junior of junior developer you have on it because you didn't see something that we're going to see in the future here. And so they say, all right, I've got no problem here. This is great. I'm just going to calculate the shortest distance. So if we start with point A, and then we decide that we're going to point at point A, we're going to find the shortest distance to the next one. That's point B. And then B, shortest distance of unvisited places is C. And then shortest distance from C to D. And then we're run out of places and we return home. Done. Solved. Hey, enjoy your trip, Mr. Salesperson. But they come back to you. Either you're the junior developer or you're the person who kind of knows a little bit more about this. And they come back to you and go, well, wait a second, the shortest distance problem doesn't work that well. For instance, I've set up this. So the shortest distance from A is going to be B, and then they're going to go to C, and then the shortest is D, and then there's only one option left. They have to go all the way over here and then return home. And that is not the optimal route. You prove that going A to E to B to C to D to A is actually more effective. So their formula didn't work, right? And it's important because here we are solving it here, but imagine somebody was traveling throughout the entire US. This could send them off days of time. This is a very important thing to get the optimal solution for. But we start to uncover something else that starts to come with this. And this is why I love this problem. It's beautifully complicated. There's this idea of traveling salesperson snowballing. So for instance, let's say we have this route and we know it's optimal. We're all happy, but we add one new city to it. Well, what do we do here? Well, it's not that difficult because what we can do is we can just go ahead and include that into the route. And it turns out in this situation, that is the most optimal route. But is that always going to be the case? Let's take that same kind of structure, but this time let's put the city right here. What does that look like? The most optimal route for this one actually look like? Wow, that changes it quite a bit. It looks very different. As a matter of fact, if you take a look here, we have where we would normally visit this city after this one, we skip it completely and pick it back up on the round back. And so that's a little confusing, right? Did anybody else kind of see that happening? And of course, yes, I do have a third example, and this one's going to be more ridiculous. Let's say that these are our cities. And we have this wonderful structure right there. We add just one more city to it. What do you think the optimal route for this looks like? It changes it completely. So we're sitting there, we're staring at this problem, we're saying, okay, finding the optimal route's being a little bit of a headache here. I have the solution. And this is the thing that I wanted to tell you all. This is the weird part that you need to really bring in. We don't see complex problems anymore because we're not in the 70s studying whether or not a computer can or can't handle it. So we actually end up not realizing when we've stumbled across something that is more dangerous, or we've assigned to someone something more dangerous. And here's the trick. You say to yourself, no problem, Gant. Computers are fast. We have clouds of gigacomputers. We're working on quantum computer. We can do anything. You know what we're going to do, Gant? We're going to brute force this problem. And we're just going to solve every possible route, sort them by distance, and take the smallest one. And at first, this looks really, really good because for there to be 4 points, there's actually only 6 possible routes, and a mirror of a route can be thrown away. We just improved it because it doesn't matter if I reverse this. If I decide to go instead of A to B to C to D, I go A to D to C to B to A. That's the same distance. So we can throw away all the mirrored versions where it goes in the other direction. But we have with these 4 items here, We only have 3 possible ways to take that because it's n minus 1 factorial. Okay, now we know we can solve them all. Let's go ahead and let's figure out how to do this. Okay, we're just going to scale up a little bit. How about 31 cities, right? That shouldn't take too long. That's 30 factorial divided by 2 solutions. That's no problem. Go ahead and solve that, kid. Come on back to me when you're done. So if a computer can do 10 to the 6 calculations a second, that means that this would be done with every possible solution. I didn't get that. In 30 factorial divided by 2 times 10 to the 6th power. And that's only 63 trillion years. That's it. We'll have your solution in 63 trillion years. That's what 31 cities. Yeah, so salespeople aren't going to like that kind of solution. They're going to be waiting for you a bit. So I want to push back against the idea that problems are solved, because this is how you feel when you come back with that solution and the computer's still just chugging away, right? So the important thing is that there are some weird hidden issues out there of some problems have fast and practical solutions, and some do not have fast practical solutions by simply doing that. One of the really cool things I like to say here is that if you could fold a piece of paper in half 42 times, take a piece of paper off your desk, fold it in half, and then do that 41 more times, that piece of paper would reach the moon. That's how much the exponential growth of that really would be. So you have to be careful. We can't confuse polynomial time with exponential or factorial time, okay? If you are folding that piece of paper in half, that's exponential. 42 times, it reaches the moon. So is this really a problem, Gant? Are you just making up pieces of paper and traveling salespeople problems? Is that all you're doing? No, this is the problem. If you can solve the traveling salesperson problem, you can solve all kinds of other problems. The truth is, people have been trying to solve this problem with plenty of other problems for a long time, because it is a problem that cannot be solved in a reasonable amount of time. It's non-polynomial time. Now, if there's a subset of non-polynomial problems that we haven't had solutions for yet, and traveling salesperson's one of those. But those are NP complete problems. An NP complete problem is the key, because if you solve one of those, you'll actually solve everything inside this space called the NP complete space, and then you would change the world overnight. You would solve you would find the cure for cancer. You would break encryption. You would do so many things, because the fact is, NP complete cannot be solved in polynomial time that we know of. And people have been trying since the 70s to figure out if they can. So let's go ahead and let's take a back off from academia for a moment here and say, like, so what do we do? What do we do when we can't have perfect answers? And this is what I love about this, is because that's the world we're going into. We've solved all kinds of problems that just were annoying, that we knew we could solve. The computational problems have been solved. But now we're trading slow and perfect for fast and good. And that is the whole concept of what we're doing with constraint programming. Constraint programming solves things like routing and scheduling and packing. Is a specific style of programming which thinks way more declarative than it ever does, pragmatic, that we usually think of for solving a problem. And what I love about this is, with the burgeoning space of AI, and this is, this isn't my AI talk, but I'm an AI fan. I wrote a book on AI. Here it is. I will talk more about that in a little bit. But this is the way we have to be thinking about problems going forward. Constraint programming. So the idea here is to define requirements, refine the strengths, refine the calculations, and optimize the results. And the weird part about this is, like, I think that as we grow as programmers and we have AI assisted programming alongside of us, we are becoming more and more constraint programmers. We are giving AI solve this problem, and then we're telling it how it should fix how it solved that problem. And this was around before people started using AI like they have this past year. So there's a really classic problem called the N Queens problem. Do we have any chess players in the chat? Let me know if you're a chess player in the chat. I'm not going to say that I'm not going to possibly lean towards you for the prizes, but I might, because it's pretty cool. The N Queen problem is a complex problem where they put queens on a chessboard. And what they want to do is they want to figure out whether the queens can or cannot attack each other. How many queens can you put on a chessboard and actually figure that out? How many can you have? And what's really cool is they have smaller, more constrained chessboards, and they say, solve the problem. How many queens could fit on a smaller chessboard? So I'm not going to tell you the answer to the N Queens problem. If you love chess, take a minute sometime, go sit by your chessboard and turn all your pawns into queens and see how many you could put on the board without having any queen being able to kill any other queen, and see how many you could actually fit on there. There's an answer to how many you can fit on a chessboard, and let's see how close you can get as you try to go ahead and do that at home. That's why I'm not telling you the answer here. I want you to go ahead and have fun with it. Alexander says 11 question mark. That's pretty ambitious. If I could fit 11 queens on there without them being able to kill any of them being able to kill each other, it'd be pretty wild. I love y'all's guesses. Y'all are pretty close. So, but I won't tell you the answer. Enjoy it yourself. You look it up, you'll see the answer in a second. So I'm not telling you here. I want you to go ahead and enjoy the game at home and then go ahead and look it up. You'll see it real fast. So let's get into a little bit of code here. Let's solve a problem that's a complex problem. And I've created the barista scheduling problem. All we're doing is running a little coffee shop, and we want to go ahead and use some constraint programming to solve setting up our schedule for our coffee shop. And to do this, we're going to add values and weights to things. And this is sort of like, I don't know if you've ever heard, but people who do routing, like for deliveries, they actually have different values depending on the turns for routes. When you do a delivery, if you take in the US, it's legal to take a right, because we drive on the right side of the road, it's legal to take a right turn at a red light or anytime. And it's really easy to do in traffic and everything like that. But left turns are more complex. They usually require extra lights. They require all traffic to stop for us to go into do a left turn. So in the systems, even though the distance is the same one way or another, our routing systems have a weighted value for right turns to be cheaper and easier, and we can do a lot more right turns, even if the distance is a little bit bigger, because it's a value system. So that's a pretty cool idea. So we're just going to start assigning values and constraints to solve this problem. And so I made the problem very simple here. We have 7 days in our week, and we want to work morning, afternoon, and night with our baristas. And we want them to be able to serve coffee. We have to have somebody working, right? And we want them to fill that schedule. Any of you who've ever worked in the food industry, like, you get your schedule posted, right? And that's just when you're going to work. Well, this is the idea of solving that problem. And it seems like it should be a pretty simple problem. But then also, I'm going to throw a little bonus on there. Each barista gets to opt in to when they would prefer to work. Because, yeah, we have to have the schedule set, but wouldn't it be nice to say, oh, I really love working nights? Okay. So now we have a complex problem with some things that are mandatory and some things that are nice to haves. And this is the fuzziness of declarative programming and constraint programming that we can kind of play in, because we can come up with a really good solution that gets as many of the nice to haves as possible while still fitting the requirements. And so I have all of the data set up. This is morning, noon, night. So this is the first barista. And this is saying on day 1 in this array, they want to work night. And then on day 2, they don't want to work. Day 3, they don't want to work. Day 4, they don't want to work. Day 5, they want to work a night. And then on day 6, they would like to work the mid shift, right? And that's how you read it. That's each of these 5 baristas, the days of the week and when they would like to work. So that's how that can be read right there, okay? I just asked them to put a 1 where they want to work and then not anything else. Okay, so we understand this. So baristas are set there and we know which one they have. So I put this into a little website and I say, hey, let's code, okay? So I'm going to take a moment here and look at a little bit of code with you. I do have all the code set up. So if we start running a little long in the tooth, I might just pull it and kind of go to the slides for the code. But I'd love to show you live just exactly what this looks like. What does it look like to think in constraints? And so if we take a look here, I'm going to pull up the website, which I have running. And we first have, I'm just going to full screen this for a second here. Here are the baristas, and here's those requirements that they wanted. They wanted to say, yeah, I want to work night. They just checkboxed where they want to work. And then here's the generated schedule, okay? The generated schedule that we get here, everybody has the same weight and the same value, so everybody works every single shift. That means everybody got the shift they wanted, but that means everybody's working. So we do not want everybody working every single day, right? So the first thing we want to do is, you can see that this perfectly fits in order, right? We have to put just a little bit of randomness inside of here, and this will help us out. So I'm taking a look at the code here. And the first thing we want to do is we're going to add a little bit of randomness. I'm going to add the cost to each person, just a small number between 0 and 1, just to make sure it breaks it up a bit. So I'm going to save that. And then if we take a look here, you can see at least now we've broken up the randomness. You don't see the same exact person and the same exact order, right? But we do have every person still working every single shift. So we think in constraint, we constrain further, right? So we can add a little bit more of the cost here. I'm going to bring my code back over and we say, should every barista work every single shift? No. So what I'm going to do is that when a shift is full, which you get by counting that shift to make sure that it has someone in there at all, then make that shift unpickable. What that means is that that person can no longer be assigned there. This is like setting the value of this to infinity. Okay, when you make something unpickable or negative infinity, actually, it's so like it can't come up at all. And so I'm going to just save this for problem 2 real quick. And then what you see here is now at least we have one person per shift. So this is a schedule. And it looks like we've solved our problem, right? But take a look at Ryan. Ryan worked 2 shifts in a row, okay? That's not what you want to have happening, especially when other people aren't getting any shifts. You want to make sure people cannot work 2 shifts in a row. So we're going to fix this problem real quick with this bit of code. So make sure a barista can only work 1 shift a day. So what we'll do is say, if we have a little check, count how many times they've had there, and we say, has been assigned today. If so, make unpickable, okay? So this, if in this particular lineup of possibility, they have already had something in that day, then they cannot be picked again, okay? And so we'll just say that. This basically is like adding the value of making either negative or positive infinity is making unpickable. So when I do that, let's take a look at our schedule now. Good. You see no one person is working multiple times today. All right. So quick question. Did we solve this? Like, is it all done? Well, no. If you can spot it here, take a look. When you take a look at a barista shift count, we can see that one person has only 1 shift and everybody else has 5. So who is that person? It's the person in the middle. John. John has one shift and everybody else has a bunch. So John got to work once and then that's it. John, we'll see you next week. Not a good plan, right? Although depending on how much, people like working, maybe it is a good plan. Who knows? So what we want to do is we want to constrain it so that we want to help out. We want to figure out what the maximum amount of times somebody should work is. Okay. And so if we go to our code and pull that up again, max fair days. Okay. We have this ability to, what would be the best way to say if we were to evenly distribute this? If this were to evenly be distributed, then each person would get the max fair days, which is like dividing into it, right? So this is how many days would be fair if everybody could have exactly their proportion. And so how do we constraint program this? Well, we could say the number of shifts worked if it's bigger than the number of like their share should be, make them unpickable again. And this should stop a person from getting like 7 or 8 or 9 shifts, right? So if we save this code here, we take a look and we can see like nobody's getting more than 5 shifts. It looks like 5 is our number. So nobody can get more than 5 shifts. And so this is a completely workable schedule, but remember I said I want a couple of soft constraints. So we've done nothing but hard constraints, things that will absolutely break the system, and it will not be okay because the cost has to come out the way that we've calculated it. But because we have these numbers, I've been using infinity and negative infinity for these things, but we could use smaller numbers for our soft constraints. And so that's a cool idea. So we're going to go ahead and we're going to add one quick soft constraint because you see, it's not really fair for, in this situation, Sharon had 3, but somebody else had 5. It would have been fair if this person gave one of their shifts over to Sharon, right? So let's go ahead and let's code that for a second. We code that. We're going to increase the cost every time a person gets scheduled. That way they're more expensive to schedule, and that should balance it out. And what we're going to do is we're going to do it by some number in between negative infinity and positive infinity. And so this says like every time they work a shift, that'll be their cost. And so a person who's been assigned a bunch of shifts will be a more expensive person to assign. And the only person they'll come up for again is when you have enough. Let me know if this tracks for you, if you understand it. But all we're doing is we're assigning a cost, and we can do it by how many times they've worked. So I'm going to hit save here. And then you see over here, we have a very balanced system. Look how nice that is. What we have here is that everybody's worked around the same number of shifts. Yes, it is true that one person had 5 shifts, but that's the only way to make this whole thing work. But everybody else had 4, right? Good question if it can only have soft restrictions. Yes, it could only have soft restrictions, but that means that nothing's a requirement. If there's like somebody has to be working that day, then you don't want it to go ahead and solve it some other way. You wanted to make sure somebody's still working that day. That is a hard restriction, but then you want to go ahead and factor in the soft restrictions. And one last soft restriction I want to bring in is that you remember these requests that they made up here above? Well, how many shift requests did we meet out of 20? 1. That's not good. Everybody gave you when they want to work, but you're not really making them happy. Yes, you are doing all the hard restrictions. Every day is covered. The company is running fine. Nobody's got too many. But couldn't you shift this around? Couldn't you figure out how many of these people you could make happy to try to give them the days and the times that they want, right? Wouldn't that be nice? One person getting the what time they asked for doesn't sound like it's a good formula. Does that sound good? No. So we're going to do one last soft restriction here, okay? And so we're going to go over here and we're going to say, where were we here? Soft constraint number 2. We're going to discount and make them cheaper on the days that they want. So we have their preferred shifts. And so we're going to do here is we're going to, if the shift that we're looking at is a preferred shift, make that person the lowest cost. Not the lowest cost, but lower. We'll divide them by this discount. And the discount I've done here is just a discount of 20, or divide by 20. Now, will this work? Will it not work? You could choose different numbers here, but this is just sort of giving you the idea. We're going to go ahead and we're going to lower the cost of them because it's nicer in the system where it's balancing out and all these things are figuring out there, to give them, if we can, the shift where they have. But the hard constraints still stop, and they're still increasing the cost depending on how much their shifts have been worked. So I'm gonna hit save here, and then we'll take a look at one last time. And we got 12 out of 20 requests. Is that the best we could do? I'm just gonna refresh because remember, it starts random. Ooh, 13 out of 20 requests. So that's pretty good. We have 13 out of 20 requests with just a little bit of code. We have 4 hard constraints and 2 soft constraints. And you notice I'm kind of using words that might seem a little bit alien at first here, but this is actually how constraint programming is like thought of. So one of the things that you see here is 13 people got their requests out of 20. The shifts are evenly distributed as most of mathematically possible. And the time it took for it to calculate this very complex problem is 0.003 seconds using our cost system that we have there. I would say this is a great schedule that we can give those people. So just to go over what it is that we solved here with the code, with constraint programming, is 1, everything was ordered input. So we went ahead and we started with a little randomness to break it apart. Then 2, we set the cost to infinity once a shift was full, and that stopped it from being able to get picked anymore. So that was your set there. 3, people were getting multiple shifts over and over and over again. So we should see if it's still pickable, if that person's still pickable or not. If not, we move them on out. Greedy shifters, we want to make sure that somebody's not getting 7 shifts while somebody's getting 1 or 2. And so what we did is we went ahead and we added the ability that there's a max amount that anybody should get. And then we went ahead and raised the cost. So this was our first soft constraint. As a person starts to get more and more shifts. So you see in this solution here, you could have 3 people with 5 shifts and then 2 people with 3. It's not good. So we went ahead and we changed it so that evens it out. And then the last constraint that we did, just to review it again, is that we gave them this opportunity to work in their discounted preferred shifts. And that's the ones that got there. And that got people to 13 out of 20 in this particular case, with all of it being distributed there. So we did it. We solved this strange, wild problem using a system of constraint analysis. And we did things, there's new terminology for some of you, which are hard constraints, which are requirements, or infinity, negative infinity assignments, or soft constraints / optimizations / weighted options. So in the world of constraint programming, you can hear this different level of terminology. Sometimes you'll hear hard constraint, sometimes you'll hear requirement. Sometimes you hear a soft constraint, sometimes you'll hear optimization or weighted option. So it's good to kind of like work with all these pieces together when you're looking at that. And so what about bigger problems? We solved this little problem with the barista store, but big companies are solving these insanely complex problems that are NP complete problems with constraint engines, and also things that aren't just NP complete, things that are just difficult to even explain whether or not they're doing well or not doing well. And so there's tools out there, and some of the vocabulary and mindset that you got today is what these tools use. There's OptiPlanner, which is Java, Kotlin, Scala, and Python. And so you can use this for scheduling, you can use it for packing, all kinds of really difficult problems. And then one of the ones that I really like, but it's weirdly hard to read, is Google solutions called OR tools. And one of the great things about these larger frameworks is rather than they have in all these optimizations they get built in, they can also, you could set them, figure out the best solution in this amount of time. Like, I don't want you to run all day. Give me the best solution you can give me in an hour. Give me the best solution you could do in this amount of time. And what's funny is they actually use AI in these systems to choose the best routes that they could possibly figure out and the best things they could get there to. And so what I did was I took our barista problem and I put it inside of OR tools, and it has some really cool features in it. One of the things it did is it found the best you can do is get 13 out of 20 suggestions. So our little JavaScript silly code that we wrote right there without an OR tool was came up with the perfect solution. The JavaScript I wrote right there can do the same thing as this huge OR tool solution can do, because it was a simple problem, of course, but it got there. And the trick is with the OR tools, it can tell you in polynomial time, most of the time it can tell you whether or not it found the optimal solution or not. So that's pretty cool. It can actually kind of tell you whether you have the optimal solution. And so OR tools told me, yep, that is the correct answer to the barista problem. The best you could possibly do is get 13 out of 20 in that setup. So that was pretty cool as well. So we learned a lot about complex problems. We learned a lot about how to sort of identify them and how to break them apart and use constraint programming to solve it. We learned about two new tool sets, OptiPlanner and OR tools. I highly recommend that you figure those out now. They're really hard to read, but you've got Chat GPT, so who cares? You can have Chat GPT tell you the OR tools code to write so that you can get perfect solutions to your problems. That's what I would do. And there's a whole world of other problems out there that we're trying to figure out what is the best solutions to get those. But it doesn't mean that we give up on trying to figure out these problems. Some of these can be solved in quantum space. Some of them can be solved in different ways. It's super cool. And we depend on complex problems to exist now. That's something that they didn't expect back in the 70s. But we need some problems to exist to be so complicated that nobody could crack it, nobody could break it, because that is how we're able to do things like cryptocurrency or encryption or SSL. If you were able to solve the traveling salesperson problem, you would be able to crack insane encryption. So the truth is, like, complex problems help stop this from happening. The real value that I'm trying to give to you today is a mindset shift, is defining problems. The future is declarative. And you can see this with AI today, because you see people go and they type in the immortal software developer in Midjourney, right? And they get something back. They're like, oh, look at that. I got something. Isn't that nice? But then you change that out to be a much more elegant prompt. And that elegant prompt turns into a much more impressive and beautiful thing. The declarative aspect of what it is that you can and can't do gives you a much more beautiful image. And I did this back in Midjourney a year ago with like Midjourney when it first came out. Today, I went ahead and took the same exact prompt and put it into Midjourney 5. And you can see, oh, look at that. That's gorgeous, right? And so while these systems are better, our system of being declarative gets more and more important. See, we are fewer programmers and we are becoming more technical guides, right? This is, of course, the girl with the pearl earring. It's a Vermeer, if you're a fan of Vermeers. If you want to talk about Vermeers, let me know. But then you have some out painting as well, which creates this just elegant artwork. We help bring that. The future's coming, whether we like it or not. You get pushed back against the idea of important problems are already solved or anything like that. But if you just take a look around, we're beset with a whole new world of really cool problems. And so with that, I think the idea is we think more declarative and we think more constrained. And that's what I have for my presentation. If you ever want to say hi to the wonderful React Native experts at Infinite Red, you will find me. I'm on the web page with the same old photo I like to use all the time. I have to say a special thanks to Mr. Brian Stearns. I reused his movie solver code in order to go ahead and do the barista problem, because I didn't do it all from scratch. It was really nice to have that. I love talking about AI. Definitely check out my book. It's called Learning TensorFlow JS. It is a book on how JavaScript can be doing AI stuff right now. And you don't have to be an AI developer. You just have to be a JavaScript developer. You have to be an engineer in your mind. And then you can start putting AI into web pages and checking that stuff out. So, like I said, check out the book if you're interested in AI. If you ever need it on a mobile device, come see us at Infinite Red. And with that, thank you very much. That's it. So, yeah, I think it's good time for questions.
Yes, we
Yeah,
have some questions in the chat.
Good. Perfect. Let me see some of these questions in chat. So thank you. I love the praise in there. I love the chat that was going on the whole time. Do you have training on the O'Reilly platform? So the only thing I have on the O'Reilly platform is my book. I thought about doing more of that stuff. It would be really fun. I would love to, but there's only so much time in a day. So we do, as of right now, I only have that book out, and we'll see. If you're ever interested, I'm thinking about doing a YouTube channel. So if you're interested in that, let me know as well. Is there a tool that solves the problem continuously improving result over time, potentially assuming additional constraints? I really like the idea of the of the OR tool by Google, which is something I would do to feed in previous results and then update it based on new information. It's very powerful. It's a little alien at first. The language and the terminology that I gave you today is going to help you really understand it a little bit better. And I think that that's going to be very useful in investigating and trying it out. And if you get stuck, just go ask ChatGPT, in my opinion. But it's weird. It's a weird way of thinking of problems, and it's really cool. But unlike having AI, which can hallucinate, OR tools can only ever give you perfectly correct computational answers. So I think that you as a developer marrying the two, kind of getting some of the concepts, getting the code, and thinking of the constraints with ChatGPT would be extremely useful, and then implementing them in a system that can only ever give you the most perfect answer that it could possibly computed on your machine or a cloud of machines in a designated amount of time is going to be a good plan between those two. I heard someone said that oh yeah, look, ChatGPT is really bad at doing math. And I was like, of course it's bad at doing math, but they solved it by giving ChatGPT a calculator. Like it's sort of like us as people, we can make up our stories, can go so far, we can calculate as much as we can, but at the end of the day, we use these tools and we have to make sure that they work together. When you're looking at AI and you're looking at constraint programming, I do see those as different hemispheres of being able to solve really impressive problems. Let's see, any other questions? Let's see, we have, can we only have soft restrictions? I saw that one during it. And yes, you can, but the problem is how many systems out there don't have a actual hard constraint? You have to have the baristas work. You can most likely solve that anyway, but you should definitely put the hard constraint. Are the any technique to manage all the coefficients so they're balanced without dominated cost coefficient? Good question. I'd have to think on that a little bit more. I'll get back to you on that. I'm not in that headspace right now. Can you recommend an online tool to play for a newcomer? Yeah. can you tell me a little bit more about that question? Just so that I know, are you looking to grow further into learning more about constraint programming, or are you looking to um, perhaps do it in JavaScript, anything like that? Let me know a little bit more about that question. But what I'll say is this: um, start using it all. Start using it all right now. Have ChatGPT open, unless, of course, you legally can't, or you're constrained that you can't, and you can't send your code to it. If you're legally bound by it, that's fine. But on your weekends and your personal projects, start working with that. Start working with image and painting. Start working with telling a computer how to give you a good solution, and start watching it get better and better at that. And like I said, I really like OR tools. I do like OptiPlanner. Like, start working with some of those as well. The issue of having to code each single imperative piece, that's going to go away. Just the same way we didn't want to do a bunch of numbers, so we created spreadsheets to help us out. And spreadsheets came out, and people are like, "Oh no, I don't trust the computer to do all that." Now everybody's got spreadsheets. Everybody has access to this higher quality of living. You're going to see the same thing happen, as like people are gonna be like, AI shouldn't do this, or can't do this, or won't do that, or you can't figure out this solution with it. Throw the whole thing away. It can't do this one thing, and until it does. And when it does, you should be there ready to go ahead and check it out. So be there, help figure it out. So I would love to, I don't see any more questions. I see some wonderful, lovely comments. And I have to say, um, can I pick the people who are going to win the 3 prizes?
Yes, yes, of course.
Okay. Well, you got it. Well, I have to say, Alexander, great questions, especially a person who's getting started. So Alexander is one of them. Vladimir quoted me, so you know that'll always get you a win. And then and Juan Telez also had a good comment there as well. So if you could do those 3, that's the ones that I'm going to go ahead.
Perfect, perfect. I just ask Alexandra and Vladimir to maybe write family names, because it will be easier for me to know exact Alexandra and Vladimir, and not try to find within all people with the same names. I had such situations, so yeah.
That's perfect.
Okay.
That's perfect. I really enjoy sharing this kinds of information. When I was in college, there was this sort of barrier to entry that people used to do with math and with complex things and stuff like that. And everybody I talked to had a pretty similar experience. There was just this issue of, this isn't fun to solve. And it's everywhere. It's very fun to solve. So one of the things I like to say is that when I was younger, I hated math because it didn't have to do with anything. And now I'm older and I love math because I see it has to do with everything. And I think sharing that and having these conversations and people showing up and listening to me talk about this stuff, I love it very much. So please connect with me. I am very interested in continuing our conversations afterward. Connect on LinkedIn and all those other places. And let's continue this chat, and let me know what you liked and what you didn't like.